Welcome to Pharmacology. So in this short section, we'll go through elimination kinetics and compartment models. And bear in mind, these are the very basic models in the pharmacokinetic parameters of a drug. So first, we go through elimination kinetics. So there are two very basic ones. First one is about zero order, and the second one is first order. So for zero order kinetics, the main principle is that there's constant amount of drug is eliminated per unit time, meaning no matter how much you take the drug, whether small amount, medium amount, big amount, the body actually eliminates at the same amount which goes out. So when you look at the graph, there's only one gradient here, meaning there's one straight line with one particular slope. So it's zero order, and most of the time this occurs when the enzyme is saturated. And under circumstance, for example, when there's overdose of phenytoin but under normal doses of ethanol, it actually follows the zero order kinetic rule. So as you can see here, the concentration time profile of this particular, in these two cases, is actually in a linear form. So these are some text about it. So so the main point here they need to read is that you can calculate it based on the Michelin's-Mitten equation, which you learn later in your later years of your course. So it's due to this slightly complicated in a way formula, but when you know it, it's quite easy. Okay, the second part here will be for zero order kinetic. So the main principle is that the rate of drug elimination is actually proportional to the plasma concentration. So meaning the more drug you take, the faster the drug elimination process would be from the plasma or the body. So it's when you look at the graph here, it's actually a curvy line here. So you can see it follows different half-life of elimination when the concentration of the drug drops. And there's a few models here. One is for single dose. We'll look through the single dose model first before we look at the multiple one in the class itself. So single dose ones, there are compartmental models which looks at the distribution, the pattern of distribution of the drug in the body. So the few basic ones, the first one compartment, two compartment, or four, or multiple. So in one compartment model, it's actually assuming that the whole body is actually consists of a homogeneous fluid, such as i.e. like you pour a powder or a solution into a test tube. So once you pour into it, the distribution throughout the whole body / the test tube will be equal at the same time. So yeah, so you have this one model, one volume VD, which is the volume of distribution, meaning there's only a single well-stirred compartment. So before you go through all the metabolism and excretion process. So as you can see, obviously this model is not very true because you're not a test tube. So anyway, these are some graphs of the one compartment model. So the more complicated one, which tries to explain in a more biological way, is the two compartment model, whereby it assumes that after administration, certain parts of the body will get the drug first before it's distributed equally to other parts of the body. So you can see here there's a central compartment followed by a peripheral compartment. So this, and don't forget the K is actually the rate of for example, in this case, rate of forward movement from central compartment to the peripheral compartment, and etc. Right, so these are the graphs related to the two compartment model. As you can see, there's two gradients here on the lines. So in the more complicated and the one that should be more accurate in a way is the four compartment model, whereby they try to differentiate the body into four sections. So the first part is the blood. Second one is the VRG, which is the vessel rich group. Third part is the muscles. The fourth one is the adipose tissues, meaning the fat layer. So as you can see here, the dose fraction will obviously be the highest at the blood, whereby we get the drug first, if you use an IV model, of course. So then the concentration will drop slowly, and whereas the same time when the concentration in the blood drops, the concentration of the drug in other sections will increase. For example, depending on the site of the anatomy site of it. like how much blood vessels are there. So when there's more blood vessels, more drug can be transferred to, for example, the vessel rich group first, followed by muscles, and obviously the last one would be the fat cells when there's least amount of blood vessels. So these are the explanation text for it. That's it for today. Enjoy!